equation, then it won't become 0, right? It won't become 0. So as you can see, if this is 0, this is 0, and these are 0, then in this case, we have 1 multiplied 2, so it will be 2. So that's a typo, actually. So actually, this plus is wrong. So this is wrong. This is wrong. So for those of you who are using the slides, then please notice this plus is wrong. So it should be 2 multiply P1 and X1 Y bar. And then similar to actually 2 multiply P2 and X1 Y bar over here. So this is wrong. And the other part that has a typo, which is this one. So we don't have something called Y bar 2. So we don't have something like that. Actually, this 2 is squared. So as you can see, this supposedly should be 2 multiply Y bar squared. So this should be squared. Okay. These are the 2 typos that we have over here. Actually, I didn't do it intentionally, but however, it's a good time to. It's a good chance for you guys to know and also try to understand that the principal point is a radial center for the density solution. So, yeah. After you modify it like that, then you will see after you put x bar, y bar, and also the r as 0, which is the principal point, then to the equation, then you will find out there's no density solution. Okay. Okay. Any question? Yes, please.
Page number 4, the principal point.
Number 4.
Yeah, principal point and the center of collimation are the same.
Yes. Okay. Good catch. Actually, I kind of intentionally not to talk about this because this will be a little bit detailed. But however, since you asked, so let's talk about it. In terms of the principal point, actually they have different principal points. So let's talk about them. Let me write it down first. Okay, so if you want to talk about the principal points, actually these are the three. These are the three. Right, so the first one is the principal point of autocollimination, or some people will just use PPA to indicate that. So in Chinese, it's called 自动瞄准相逐点。自动瞄准just is the autocollimination. So 相逐点 principal point. So that one is this one is the G over here. That one is the G. So collimator, right? So the principal point of autocollimator means this one. This means the location of the G over here. Right, that one. And then the next thing is the principal point of autocollimination. Actually, it will be close. It will be close to these two. The first one is the indicated principal point, or IPP. This is called 光标标示相逐点。光标标示相逐点 indicated principal point. So the IPP is, as you can see, we have fiducial marks. We have fiducial marks, and we also have these cross. So we can connect them, and then we can have one principal point over here, and that is indicated by the fiducial mark. So that is IPP, indicated principal point from the fiducial mark. So IPP is defined by the fiducial mark. Okay. Then the next thing is the calibrated principal point, or so-called principal point, the point of symmetry. Point of symmetry. So PPS, S means symmetry, point of symmetry, and this is called 预定相逐点。预定之后的相逐点。Okay. So calibrated principal point, right? So as you can see, that is indicated over here, the O over here. That is the which is indicated as the principal point over here. That's the O. So the idea or the rule for this calibrated principal point. So as you can imagine, okay, say the first two are easy to understand. The first one, the PPA, that is from the multi-collimator. So the center one, that is the location of this PPA. IPV is also easy because you connect the fiducial marks and you can obtain the IPP. But how about PPS? How did we get the O points over here? How did we get the calibrated principal points? And that actually links to the answer I give to Senwin's question. So basically, this is the principal point that we defined to obtain the best symmetry. That is the point that we try to obtain the best symmetry. Okay. So and I also mentioned it yesterday. Say actually the how to derive these principal points. The procedure is a little bit it's too complicated. It's not too it is complex. So I'm not going to talk about that in this course. But if you are interested, you can take a look at the textbook or the reference book that that is for this course. So basically, the principal point, calibrated principal point, is the point that we defined, and along with the calibrated focal length, to get the best symmetry for the lens distortion. So that is the three types of principal points. Yeah, just like that. Hey, does that answer your question?
So they won't be from the same location.
They could be. It could be. They will be very close to each other. They could be the same point. But however, they may not be, and most cases they won't be the same location. Yeah. Okay. Why they are not the same location? Symmetry error. Systematic error. From where?
From the lens.
From the lens, or from your image plan, those things, and from your fiducial mark. Those could be the source of the systematic error to cause this type of problem. But I probably won't call it a problem. It's just whatever is made by human has error, and these are the error. And mainly, we regard it as systematic error, but it also includes the random error as well. Every time you work on the same type, same model of the camera, their behavior, their detail are different. So yeah, that's the case. Okay. Okay. Any other question? Before we move on. Alright, if not, then let's move on. Alright, so this is mainly for the focal plane unplannedness, and like I said, nowadays actually we don't really care too much about this because we have the CCD array and also the CMOS array. So that's well, it's pretty flat. Okay, and actually, so yeah, you don't need to like take this part very seriously, but that was a big deal in the past. Okay. Alright, so let's talk about the field method. So first of all, okay, before we talk about the field method, let's kind of review the process of the laboratory method. So from the laboratory method, as you can imagine, in order to understand the camera's lens distortion behavior, what you need is you need ideal answer. You need an ideal answer. So from the laboratory method, the ideal answer is from the multi-colorimeter and also from the focal length, and mainly from the multi-colorimeter, but also from the focal length. So once you have the focal length and the multi-colorimeter tell you that for each of the angle is 7.5 degrees, so you can calculate the ideal answer. And after you have the ideal answer, you will compare with the real observation, which is the mean distance to each of the angle. So with that, you can obtain the lens distortion. So, which means that we need ideal answer, and we need to have the current answer and compare their differences. And finally, we can obtain the lens distortion. So that concept applies to the next two methods. The field method, as you can see, these are the steps for the field method. The first one is the control field setup. 控制场, control field, in Chinese is 控制场. So how to set up the control field? So basically, like I said in the past, you need to choose a field, a specific field, and then, for example, I can choose this wall as the control field, and I set up some marks. I set up some features, some marks over there, and then I just place it on over this wall. And sometimes some people will choose a corner, for example, like this, so that you have one plane over there, one plane over here, and also you have the ceiling. And also you place those marks, and then like sticker, you just stick to the wall. And the second step is the control surveying. The control surveying is about, right now, those marks, they will serve as the ground control points. Those marks, they will serve as the ground control points. So in order to create, or in order to obtain the ground control point, we need to measure its coordinates. So the control surveying is about how to measure each of their coordinates for the marks that you just set up. So maybe most of the time you will use the total station. For those of you are working on the surveying practice TA work, then you guys should know the surveying. You guys should know the total station, which is an instrument. For those of you who may not know, which is an instrument, and it's an instrument that allows you to measure the angle. For example, like the vertical angle or horizontal angle, and also sometimes measure the distance. Okay, so that's some instruments for the surveying. Okay, so you will set up the total station and then measure the coordinates for each of the marks that you set up in the first step. Okay, that's the control surveying. The next step, picture taking. The picture taking is simple. You just have your camera, the camera that you want to calibrate, and then you come to the field and then find out the location of where you are going to set up your camera. And then here, which means that you need to know the EOP, or you need to know the EOP of your camera. So you set it up over here, and then take a photo. and that's the third step. Then after you take the photo, you have the photo, and then you can start measuring the image coordinates for each of the marks. So you have the image, right? So for each of the marks on the image, then you are going to measure its image coordinates, each photo coordinates or image coordinates. Okay, so that's the fourth step. Finally, you can perform the mathematical modeling. So what does it mean by the mathematical modeling? Let's talk about the concept first. So you can imagine, right now, what we have is the object space coordinates for those marks. And right now, we also know the EOP. Then, supposedly, we can perform back projection or reprojection. We can reproject those points, those marks, to my image. And so, if I have a perfect camera, then which means that my principal point, my image coordinates, and object space coordinates, they should be collinear. So it must follow the perfect collinearity condition equation. It must follow the perfect collinearity condition equation. So that means we use this answer we use the ground control points that we just set up to obtain the ideal answer. To obtain the ideal answer. Okay. But however, compared with the image coordinates that we just measured, we will find out there are some differences, and those differences are caused by lens distortion. Right. So the final step, mathematical modeling, is about how we can how we can set up some additional parameters to the collinearity condition equation. Then that's something we talked about before. So the simplest